Good afternoon, everyone, and thank you for attending this first distinguished lecture of this year. And it's my great pleasure and honor to introduce our speaker, Dr. Sanjit Kumar Mitra, who is Research Professor of Electrical and Computer Engineering, University of California, Santa Barbara, and Professor Emeritus of University of Southern California, Los Angeles. Dr. Mitra's talk today is entitled Digital Signal Processing, Road to the Future. Dr. Mitra is internationally known for his work in analog and digital signal processing and image processing. He's published more than 700 papers, authored or co-authored 12 books, and holds 5 patents. He completed his undergraduate work in physics with honors at India's Utkal University. His brother then talked him into shifting to electronics, which then was a new program at Calcutta University, where he earned his master's degree in radio physics and electronics. He then came to the United States to complete a second master's degree and PhD, both in electrical engineering at UC Berkeley. He followed in the footsteps of an uncle who had spent a year there on a Fulbright. After completing his doctorate at Berkeley, Dr. Mitra became an assistant professor at New York's Cornell University, where he created a course on the use of active analog filters as integrated circuits. This was one of only 2 such courses in the United States at that time. He joined then UC Davis College of Engineering, and go Aggies, yes. Oh, Bell Labs, we missed that, I'm sorry. He joined the UC Davis College of Engineering in 1967 and soon restructured the junior level course in analog and digital electronics. He created a novel lab component and developed videotaped self-instruction modules. After 10 years at UC Davis, he transferred to UC Santa Barbara, and this was in 1977, where he established a matrix laboratory-based undergraduate course on digital signal processing, complemented by an innovative lab section. He subsequently rose to become chair of that department in electrical and computer engineering. He joined USC's Department of Electrical Engineering in 2006 as a member of the university's internationally renowned Signal and Image Processing Institute. He's earned many honors. The IEEE James Mulligan Junior Education Medal in 2006, which honored his outstanding contributions to electrical engineering education through pioneering textbooks, innovative laboratory development, and curricular reform. His many other honors include the IEEE Millennium Medal, the European Association for Signal Processing's Technical Achievement Award, and the IEEE Gustav Robert Kirchhoff Award. And that latter award was for his outstanding contributions to the fundamentals of filter design and signal processing. He's also a fellow of SPIE, IEEE, and AAAS. And finally, he is also a member of the National Academy of Engineering. He's held many visiting professorships throughout the world, and some of these include in Australia, Croatia, Finland, Japan, Turkey, and the United Kingdom. So in final, we are again very honored to have him here, and please join me in welcoming Dr. Mitra back to Davis.
Would you put that in writing for me?
Absolutely.
My wife doesn't believe. She thinks I goof. So, anyway, it's a pleasure to be back. And as Dean pointed out, I was here for about 11 years. My friend Ralph Algazi has shown up. So Bernard, I'm having breakfast with you tomorrow, right? Okay. Anyway, we can talk about it. But let me tell you before, because Ralph is here, he and I started the DSP course here. Ralph, do you remember? And what happened, just to brief, my original background was analog circuits, actually designing filters without inductors. That was my PhD. Then I continued working, and I had grants here, but I was getting bored doing the same thing, writing papers. So I terminated my grant. Ralph may not remember. My program manager write down the proposal. I said, I don't know what I want to do. You have to wait. So I decided to work in the company, and the only thing I don't want to do filter design, analog circuits. So Stanford Linear Center, I got a position for the summer, and they had built the test equipment reading a paper, but it was not doing what the paper said. So my job was to model it on a computer, then tell them what changed. Unfortunately, in 2 weeks, I got a very good model. I could repeat their result, the paper's result, and everything. Then the rest of the summer, I had nothing to do. So I went to the supervisor and said, is there anything else I can do? I said, do you know digital signal processing? No. I said, why did you ask? Oh, I hope you give some lectures. I will give you lectures. Just give me some time to read. Fortunately, it was very beginning stage of DSP. Only one paper, 2 papers, I think the book, short book. I loved, get 4 lectures, come back to Davis. I think Hurst Loomis was chair at that time, right? I said, I'm going to teach DSP. So I talked to Ralph. We taught this course for many, many years, I think. So thank you, Ralph, for your help. So that's how I got into DSP. Okay, second thing, this catchy title, let me tell you the story behind. This European Circuitry Design Conference was to be held in Helsinki. So the conference chair said, invite me to give a plenary lecture. I said, so I sent him a lot of catchy titles, including this one. He picked this one. Then I wrote to friends all over the world, what should I tell? What should I do? Fortunately, everyone, it sounds good, why don't you come and give it here? So I gave many lectures like this before I went to Helsinki, but it's still, every time I give, the audience gives me some new ideas, I keep adding. So, okay, that's the end of the story. About 2 jobs. I retired from UC Santa Barbara in June 2006, because if you work 40 years, you retire at full salary. So I thought a good time. And so I gave hint. My daughter is a professor at USC, electrical engineering. And she gave us a grandson after many years. So we used to go to LA quite often. And Max Nikias is Dean of Engineering. You may not know, he's a signal processing person. So he called me to have lunch, and by the time we had lunch, he has become provost. He made me an offer, I couldn't say no. Finally, it would have been stupid of me not to accept. Only thing I said, Max, I'll do half-time. Fine, my offer stands. So for 6 years, I was there half-time, 3 days in LA, 4 days in Santa Barbara. And then I want to write a couple of undergraduate books. I found it very difficult because they're different kind of books. So I decided I should retire again. And fortunately, USC, if you work 50%, you get retirement pay. So that's why I have 2 jobs. And they're still very kind to me. They still pay a lot of my travel and everything. So they've been very good to me. Okay, that's about it. So this lecture is at a level hopefully everyone can follow. And up to okay. So quickly, DSP actually goes back to 17th, 18th century mathematics, but it has become a very important tool in many science and technology fields. Techniques and applications go to as old as Newton and Gauss, and as new as digital computers and integrated circuit. Basically, digital signal processing, the signals are represented as numbers. You process them, generate other set of numbers, which hopefully has better properties and better characteristics than what you're putting in. Okay. The main thing, everything is digital, so you don't have drift in the filter characteristics. Processing is fixed. Binary coefficient as number, independent of external environment and aging. Unlike analog filters, which have these problems. Is there any undergraduate students here? Okay. I used to do analog, but I couldn't do integration. So that's why I went to DSP. It was in product and sum. Very simple. Okay. And then you get quality very improved. So if you add 1 bit, you get a 6 dB improvement in signal to noise ratio. You can reproduce, they're all digital circuits, so it could be reproduced. Component tolerance has no effect, no adjustment, no realignment over the, so there are a lot of, and then other things, DSP also allowed us to develop a lot of new things, which could not be done in the analog. Okay? Multiplexing, we can take many signals, multiplex them, use the same system. We can change the system by changing some of the coefficients, so the one system can behave differently for different signals. So that made it cheaper. And again, we use standard digital circuits for implementations. So everything was known. Early days, actually, the computer was primarily used by oil companies. For a long time, we did not know how advanced they were, but they don't publish. Later found out they have done a lot more things than we knew. And so this, I'm not used to this. Okay. The main thing that you could not do, you're using batch processing computers, so you could not do real-time processing, but computer allowed a lot of flexibility in processing. Original work was basically how do you program a digital filter in a computer, so you have to do approximation of analog filter. You need A to D, then you do filtering, then you need D to A to convert back to analog form. So DSP algorithm development with the approximate or simulate analog signal processing. Then people started learning more and more, and so they got sophisticated DSP algorithm, and some new algorithms had no analog equivalence. Unique algorithms like capstan analysis, homomorphic filtering developed at MIT, and these algorithm implementations require precision and resolution you cannot get with analog circuits. And then came FFT, or fast Fourier transform, which was rediscovered in 1965, and FFT reduced computation time of DFT by orders of magnitude, and then we could implement sophisticated signal processing algorithm with processing time so that could do real-time interaction. FFT inherently discrete time concept. So all of this got people interested to look at DSP as a discrete time, not taking analog and converting it to digital. Okay. So the new algorithm was adaptive digital filtering, multi-rate digital signal processing, mixed analog digital signal processing, nonlinear digital signal processing. And then how DSP has evolved. In the 60s, basically when we got involved, late 60s, MIPS cost was $100 to $1,000, then military got into it, cost of MIPS was down, and now it's probably about a penny for MIPS. Performance started improving, and as price fell, a lot of new applications started coming. And so here, a chart from Texas Instruments, how from 1980, eventually 2000, how more and more algorithms are being implemented in DSP. Okay. And major application is in communication. You can see how this has changed. So this is old, but roughly still the most of the application of DSP in communication. You have your cell phone, could not be done without DSP. Okay. And military also, military actually pushed it as far as it can. Okay. And they're still used, and in fact, now your cars have so much computer and so much DSP is unbelievable. Okay. So I'll go through some of these examples quickly. What time should I end?
Quarter till, just in 10
Okay.
till later.
Okay. Yeah, anyway, so then I'll skip some of them, but these are some of the things I wanted to talk. So what I will do is I will skip some of the top ones. And then this is something very unique. It cannot be in the analog. And so this is something, and this is another thing I want to talk, because this was started by one of my former PhD students. Then digital camera, we did a lot of work for a company. Then sound synthesis, then software radio. I'll skip digital television, so let me go. This is still, I think, extremely important still, even though the quality of speech improved a lot, and a lot of them are done by AT&T, is when you talk to a computer, you don't know. The voice is almost like human voice, even though it's generated by a computer. And this, I still think there are a lot of work still to be done. And speaker recognition, still a lot of to be done. And most of them, I think Ralph, you worked in this area. Yeah, so Ralph probably is a better person to tell you, but still the difficulty, the vocabulary size is still limited. Recently, I heard a talk from Microsoft also. They have a new software where they can even catch emotion of people, which I thought was very interesting. I'd like to learn more what they have done. Okay, cellular phone is probably the biggest market, and you can see there are over 7 billion phones now, and particularly in developing countries, underdeveloped countries, it has become a huge advantage. And many countries, they are benefiting having cell phone. And in fact, one of the persons who did a lot is Andy Viterbi. And so I will talk about him. If you know, I can tell you about more about him. Incredible person. So this is basically a block diagram of a cellular phone. You can see the big part of it is DSP. Okay, this is one of the chip designed by Texas Instruments. This is something I would like to talk to. This is something I don't know whether any textbook has. It's in my book also. It's a purely discrete time-based technique. And the core technology in the implementation of asymmetric digital subscriber line and very high rate digital subscriber line. And this is related to orthogonal frequency division multiplexing, OFDM. ADSL is a local transmission system designed to simultaneously support 3 services on a single twisted wire pair. You know, your cable coming in the home is plain old telephone service, but the data transmission downstream toward the subscriber is a bit rate up to 9 megabits per second and upstream to about 1. But these numbers can be different I know Europe, they're pretty high. I don't have the numbers with me. This is roughly the block diagram how frequencies are allocated in ADSL. This is typically up to about 3 kilohertz, then low bit rate upstream, high bit downstream. But I want to show you a block diagram. A VDSL is an optical network emanating. There's still a lot of problems here because the optic to going to regular cable is a problem. And you need good adaptive filter, but you can't have too many taps. Okay. So here's the block diagram. Everything is digital. So you have a digital symbol input, demultiplier, and it uses IDFT, then parallel to serial converter, then channel is analog, so it has to be converted into analog signal, then converted back, and it was originally proposed by 2 IBM professors, trying to forget his name, Pellet and Ruiz, I think the other guy's name. It's a beautiful, beautiful mathematical thing, a concept. And if you want to know, it's in my book also. So, okay, DMT, the advantages, you can see, main thing is it's very easy to adapt to channel conditions. You don't have to build a fancy adaptive filter, okay? Because you're looking at the samples which are coming, and you can do approximate channel equalization so you can get reduced sensitivity to line conditions. WaveDIM is similar to, in fact, we have now digital radio. And Europe, they had digital radio about 10 years back. And what is the name of that company? Every car you buy has that digital radio if you want to pay. Okay. Okay, I would like to talk about this. This company was started by my former PhD student and some of his friends. Basically is you need high power RF amplifiers, which is a big part of cellular and PCS base station. And the cost of that is typically 50% or more, and it takes a lot of power in the base station. So the idea is the link amplifier. It was originally proposed for analog, and there's a letter to the editor proceeding in 1930s, but it could not be built. Even the concept is very simple. So the idea is you have your signal coming, which is like amplitude modulated signal, then you separate it into two complex signals. So they have a constant amplitude, okay? And since they're constant amplitude, you can go to amplifier and go in the nonlinear range, high power. And since the amplitude is constant, doesn't matter, then you combine it and get it back with a high power using nonlinear part of the amplifier. And they built it. I think I have their block diagram. This is their system. Unfortunately, after 9/11, they didn't get any more funding. So they had to sell it to AT&T, not AT&T, Bell Labs. But it was started by my student. Okay, I'd like to tell you a little more. I need the screen down. Show you some of the work we have done for a camera. So original cameras had CCD sensors, so you need a CCD sensor and a CMOS chip to do all the image processing work. And then many companies thought it would be nice to have a CMOS sensor and the integrated circuit, everything could be done in a single chip. So we worked for a company and the way it is done, most cameras you have a single sensor, typically half the pixels bring up the green, because his green has most of the amplitude, and 1/4 red, 1/4 blue. So once you get that, then you have to interpolate and can you get the drapes down, please? Yeah, I have a couple of images. Light also. Thank you. I hope it works anyway. So idea is you have to find half the missing green pixels, 3/4 red, 3/4 blue before you get the color image. Okay, so first you have to do color interpolation, and then then you have to do bad pixel, because sometimes transistor doesn't work, so some of the pixels looks like impulse noise. The problem with that is as the chip gets hotter and hotter, the amplitude of the bad pixel, the impulse changes. So you have to have something which can adapt. Then you do color interpolation, and the color you get after you do is not the color you are seeing with your eye or the camera sees. So you have to do color balancing. Then of course you want to do contrast enhancement. And when you do all this, you get false colors. You have to detect and mask. And after that, you do compression. So we did most of this for one company. And after about 5-6 years, they decided to drop the whole thing. But anyway, companies here work differently. But the only thing I want to tell you that we gave many algorithms. The one we thought was the best, they didn't use because it's too expensive. The one we thought was the worst, that's what they're building because cheap. Okay. So here is from their camera, you can see these white dots. Those are the bad pixels. I put a circle here to show. Though, just imagine. So this is actually what the camera sees. Okay. Then you mask those pixels. You can see we got rid of all the bad pixels. And ours is like an adaptive algorithm, so it will keep on adjusting. Then you do color interpolation. This is what you get. So now you have find the missing green, missing blue, missing red. But this is not actually what color you're seeing. So you have to develop an algorithm, because these are charts, I forget the name of the company, behind each square that tells you what are the RGB values. So you develop an algorithm to match that. So this is what we did, okay, for them. Okay. So there are a lot of techniques we have done for them. Okay, this is something also interesting, DSP application. There are 4 different methods: wavetable synthesis, spectral synthesis, nonlinear synthesis. You can have the screen up and down, doesn't matter, because I don't need it anymore. And then synthesis by physical modeling. Now most of the work is going on physical modeling. So wavetable synthesis, you record or synthesize musical events, you store them in internal memory and play back on demand. Then you can do some playback tools like pitch shifting, looping, enveloping, and filtering. Spectral synthesis, there are several different methods. One is you produce this signal sounds from frequency domain models, and basically you represent the signal as superposition of basis function with time varying amplitude. Practical implementation consists of combination of either additive synthesis or subtractive synthesis or granular synthesis. Oops, what happened? Okay, I pressed the wrong button. Nonlinear synthesis is a frequency modulation method, time-dependent phase terms in the sinusoidal basis function, and this is typically what you find in your PC sound card. Oops. This is probably the most interesting work and going lot of work going in Stanford, CCRMA. Julius Smith, a very nice person, has done a lot of work. And it models the sound production method by partial differential equation, the main vibrating structure, and most methods based on wavification describing the wave propagation in solids and air. So these pieces came from Stanford. Oh, again, I made a mistake. Oh, God.
I have a question.
Yeah.
When you say modeling the main vibrating structures, for the saxophone example,
Right.
Does that include just the reed, or are you also modeling all the acoustics and the whole structure? of
I'm
the
not an
instrument?
expert. I'm just telling what they told me.
Okay.
Okay. Okay, future trends defined by market trends, defined by particular implemented specific products, so what products will dominate in the future. Actually, this slide was done before iPhone came. So future products dominating the market will be computers and cellular phone. It will be difficult to separate between these products. Cellular phones will have computing powers, and computers will need mobility and mobile internet access. So what we need with computing, what handsets with computing capabilities and mobile connection to the internet, we need multimedia services instead of simple phone calls, and global mobility with multi-standard capability. You need flexibility of terminals, up to configurability in real time by the networks. So basically, you can see we need all of these. So finally, we need the software radio. Okay, there's still not much happened, even though there was a lot of hype maybe 10 years ago. So we're not there yet. So software radio, the aim is to build a flexible, multi-service, multi-band, multi-standard radio system that is reconfigurable and reprogrammable by software. Reconfigurability is provided by the DSP engine reprogrammability. Two main goals must be met: move the border between the analog and digital worlds towards radio frequency, and adopt analog digital converter D to wideband converters as close as possible to the antenna, and replace all the ASICs with DSP for baseband signal processing to define as many radio functionalities as possible in software. Okay. So replacement of ASIC technology with DSP enables software implementation of baseband functions such as coding, modulation, equalization, pulse shaping, and reprogrammability allows multi-standard operation. Okay. So this is roughly the block diagram. In fact, Gerhard Fettweis was involved a lot, but I think he has stopped working in this area, as far as I know. So this is a roughly block diagram of a software radio, and you can still see there's a big DSP part, but there are some specific circuits which is better to independently realize them, and these are called accelerators. And so these are, the number crunching are called accelerators. And like digital down conversion, Viterbi equalization, the spreading, digital filtering, digital down. So these are the examples of accelerators. Unsolved problems. MPEG-4 still has not taken over because it has been very difficult, robust object extraction. There are a lot of papers, but still you cannot repeat them. Existing algorithms are robust and work only under certain conditions. So until we have a simplified and robust algorithm of object extraction, MPEG-4 will never become practical. Co-channel signal separation for wireless communication. Since multiple users occupy same channel, signal processing algorithm needed to separate and demodulate the user signal, preferably with low complexity and low noise enhancement, and we need these for both TDMA and CDMA signal formats. We need blind adaptive beamforming or space-time array processing. We need adaptive antennas capable of nulling signals without the use of training or pilot signal, and they can be used in wireless communication and the global GPS applications. Okay. Adaptive equalization has been applied to wireless and wireline and wireless communication since 1960, and current applications include next-generation multimedia wireless network as cable and digital subscriber lines. Filter banks for source coding have been studied extensively in the past. There are still important applications when it involves non-stationary signals such as video and motion picture. Compression is used in motion picture signals in editing systems so that films can be edited digitally without requiring massive amounts of data storage. DSP chips for the future, very low power consumption, high speed operation. You need reconfigurable processors. Some applications you need a customizable processor, and you need DSP chip with multiple integer and floating point MACs. Reconfigurable MAC array with embedded memory for high-speed processing, vision, and video processing. As many DSP algorithms are dominated by fairly well-structured inner loops, this approach has the potential to combine the flexibility of a conventional processor with the efficiency of a custom hardware. Customizable processors are not field configurable, but can be customized by the system also chip designer to better meet the needs of the application, and can be very effective for certain DSP applications. DSP chip with multiple integer floating point MACs, multiple ALUs will allow simultaneous dispatch of many operations per clock cycle, and some of the chips available are Equator MAP and Sun MAGC. Okay. Major bottleneck, we still need high-level language, and we need efficient compiler. And you can see how DSP integration has changed from 1980. The die size has remained, but the wafer size has gone from 3-inch to 12-inch. And number of transistors in a chip could be over 50 million. Okay. Power dissipation has gone down. DSP is impacting the way we work, we live, we learn, we keep information, we play, we travel, and we socialize. Very quickly, some of the future device, and I'm pretty much thinking this is still not yet. And this one, I got interested, I'll tell you why, but nothing has happened, and we gave it up after a while. Quantum cellular automata, nanotubes, this I think has a lot more future. Quantum computing, maybe, I don't know, but okay. Quantum cellular automata is a nanostructure compatible computation paradigm, uses arrays of quantum dot cells to implement logic function, and a 3-input majority logic gate based on QC has been reported. This came from Science 1999. And the majority gate can be programmed to act as an OR gate or an AND gate. Information transfer procedure, use of currents, that is transfer of charge is in conventional digital circuit, but in the quantum dot cellular automata is propagation of polarization state from one cell-like structure to the next. Okay. Advantages, offers a fast switching and low power computing architecture. In theory, architecture can be shrunk to the molecular scale. The disadvantage is works 0.1 Kelvin. Okay? So this is probably a big bottleneck. Smaller cells should allow an increase in the temperature of operation. This looks very interesting, and magnetic quantum dot cellular automata is a promising approach to quantum computing, and a universal logic gate has been built based on magnetic nanostructures and makes use of spintronic built on classical ferromagnets. Okay, let me go with, I think, this. Nanotubes, I think it was discovered in Japan in 1991. Roughly 1 billionth of a meter in diameter, 500 times smaller than today's transistor, potential use in nanoelectronic devices. Field effect transistor, based on a single carbon nanotube. It consists of one single wall carbon nanotube connected to 2 metal electrodes. By applying a voltage to a crossing tube, the nanotube can be switched from a conducting to an insulating state, and it can operate at a room temperature. What is needed is an inexpensive approach to densely packing nanotubes onto silicon wafer. The difficulty is when you deposit on a silicon substrate, you get a tangle of both semiconducting nanotubes and metallic nanotubes. So to build devices, the metallic nanotubes have to be eliminated, and you only manipulate the semiconducting nanotubes. Okay. So one approach, I think it was IBM, disperse a tangle of nanotubes on silicon and fabricate electrodes on top. Using the electrodes, switch off all the semiconductor tubes so they cannot carry a current, then selectively shatter the metallic tubes by applying a voltage. And this was the IBM, I believe. So remove concentric layers of nanotubes that are rolled up inside one another, and by sculpturing such roll of tubes, it may be possible to build transistors with desired properties. Approach used at IBM was to fabricate a large number of nanotube transistor on a chip. And this shows a regular area of source, gate, and drain contact randomly deposited silicon. So I'm going to expand this part right here. So electron microwave enlargement of the second and air center shown below. You have a source, a drain, and a gate. So a branch like a nanotube can be seen running from source to drain. And this, I believe, was done at Delft. A single electron transistor comprises a small island of discrete energy levels, a quantum dot and molecular structure connected to metallic leads by tunneling junction. A room temperature set has been reported. Okay, it is. I'm going to skip quantum computing. I'd like to briefly tell you about default hardware. When it came out, it looked very interesting. Basically, normally when we build a circuit, we go to a computer, we optimize until we have the final circuit. But here the idea is the chip will do everything. Okay, so basically you need something with a lot more connection than. And in fact, I submitted a proposal to NSF when I was here. And one of the reviewers didn't like, so why don't you remove this? But we had the same idea in the proposal. So I regret not keeping up working in that. So evolve and learn to improve yourself using trial and error experiences. You seek solutions through trying billions of different possibilities, continually crop and refine your search algorithm, and every time you select the best each time and tries that. Everything is done by the chip. Okay. So you need reconfigurable hardware. The trick lies in creating a device that knows how to make the correct structural adaptation at the correct time, and it uses a genetic algorithm. This is about 40 years ago. So the design steps is basically a set of random blueprints which are used one by one to configure the device. After each reconfiguration, the device is tested to see how well it carries out the required task. Highest scoring designs are retained as guidelines as parents for new generation of designs. And the offspring designs are created by swapping portions of the parents' blueprints with one another or making some random changes. The marginally improved population of design then undergoes further testing. Everything is keep on doing by the circuit until it gets the optimal level of performance. Okay. So entire genetic algorithm, blueprint creation, fitness evaluation, reconfiguration can be contained with a single microchip. And at that time, a Japanese author claimed they will have evolved hardware in the future, cell phone, but I don't think they have come out yet. It was done both discrete time and continuous time. I got interested. I had a student look into it, and finally decided we don't want to get involved. This was actually, there were a couple of papers done from England that they claimed the analog circuits could not be designed using theory. But again, I haven't seen anything coming out of this professor since they published this paper. Okay, I have to give credit to many people who helped me prepare this. Jeb Beer from Berkeley Design Technology, Giovanni Guidotti from Marconi, Jean France, he has retired from Texas Instruments, Fred Wang from Georgia Tech, Jim Kolonek was my student, Takao Nishitani used to be at NEC, then he became a professor at Tokyo Metropolitan University, Rudolf Rabenstein from University of Langen-Nuremberg in Germany, Masaru Sakurai from Toshiba Corporation, John Singh is my colleague, and Takao Yamaguchi of Sony Corporation. Takao spent 2 years with me. Masaru also spent 2 years with me. I used to get a lot of engineers from Japan come and spend a couple of years with me. So that is the end. I hope I'm on time, and I'll be happy to answer questions. So.
Take some questions, Dr. Mitra.
Yeah.
Okay, the way digital signal processing is taught is essentially based on von Neumann computing type of model. But a lot of the architectures you're describing now are not at all von Neumann. Not only quantum computing, but cellular computers, neural networks, anything. So that means that all the remapping of the DSP algorithms
No longer, you're right.
has to be done, and DSP maybe has to be taught differently.
Right. The big thing about quantum computing, everything, I talked to some of the people, if you read literature, the biggest funding comes from military. They're interested in creating the codes, not error correcting, codes which cannot be decoded very fast. So longer is the code, and that was their aim. But the big problem, in my opinion, I talked to many people, how do you get data in? Getting data out is known. So until that is solved, it will be very difficult to use it. And military is also interested in DSP applications, because they have pushed the DSP, in the beginning, they pushed a lot. Okay. By the way, I gave up DSP a long time back. I have a habit of getting bored with the areas. So in fact, Ralph also used some work on image processing. I remember in Scotland, Glasgow, you had a paper. So anyway.
another question.
Yeah.
You mentioned that DSP could be used in a multitude of fields. What are some of the other
That is,
fields?
no, well, DSP is used in medical applications. I mean, original application DSP was looking for oil. Okay, you put a lot of, what do you call them? I forget all the terms. And basically they create, what is it called, Ralph? The sound goes through, comes back.
Oh yeah, they were acoustic propagation with
Yeah.
an array of sensors.
Right.
An array of sensors.
And they can analyze and see which kind of rocks there are and where oil could be. In fact, oil people, they're very secretive. And a friend of mine used to consult, he won't tell me what he was doing. And we found out much later they were much more advanced than we were. Okay. Particularly in two-dimension DSP, they were much more advanced. Okay. So, but it's going to everything now. You go to, in fact, your washing machine and everything. They're creating, and also that people can talk to you rather than you doing it. And they have to find ways to make money. And the idea, in fact, Jerry Suran told me, originally when they're using ICs, they have 1 or 2 chips in a television. But I said, this is a good selling point. Okay, and that's what they are going to do now. Okay, because the book thing in DSP also, your books, e-books, So, in a way, it's very mature field. The lot of work still going on in multi-rate. In fact, one of my former students, P.P. Vedanathan, he, by the way, got the Kirchhoff Award. I nominated him just this year. He'll be getting it next year. Very bright student. He's a professor at Caltech. He's probably a leader in multi-rate now. So multi-rate. And the other area is also one of the big problems I find, I have talked to many people, that you cannot just take 1 dimension, go to 2 dimension. That's number 1. And second, people are trying to get faster and faster A to D, but they're coming to a point it cannot be done anymore. So I advocate and the way people are doing, again, in my opinion, is wrong. They take an analog system, they want to do exactly the same in DSP. I said, why don't we think maybe there's another way of doing the same thing? And so whole discrete concept, and in fact, P.P. Vaidyanathan's work is a very famous, actually, Alfred Fettweis, he passed away a few years ago, one of the brilliant men I have ever met. His idea to build low sensitivity digital filters, take an analog filter, component by component transfer to digital domain, he called wave digital filter. Okay, it's based on the scattering matrix description. And when I was at Santa Barbara, nobody wants to take analog circuits. I used to teach, finally I gave up. So my idea is, can we do Fettweis's work building the digital domain, not doing analog circuit theory? So PP came up with this idea, and Fettweis is a small part of what we have done. And it took me a long time to convince Alfred what we have done is more general. Okay. But the problem, again, I think, is people, to get high speed, we can do parallel processing, which has not been done much in many areas. So I organized a workshop in Switzerland many years ago, got some people to come. And Paul Gray at Berkeley has done a lot of work on high-speed A to D. I said, Paul, you're coming to, you cannot do anymore. Maybe we should look at, can we get a different algorithm to implement? The whole system you have to think together, not block by block. But we're not doing it. Okay. So anyway, I retire, so I don't have to worry about these things anymore.
How do you see the human and this machine interaction? Will the intelligence be transferred to machine from human in the future?
This is a very big area. In fact, one of my colleagues at USC, Sri Narayana, millions and millions of dollars for every agency. And it's basically like LA has a lot of ethnic population. They go to doctor, and doctor by talking can understand, but sometimes they don't know how to interpret that. So his idea, can computer be used? Now, autistic children, how do you communicate? So he has lots of funding. And this is what I thought Microsoft new software may help. And because I don't remember the exact name, but a lot of them doing is, how do you extract the feeling? Okay? And human-machine interaction is still at a very primitive stage. Okay? Because particularly it will be useful in medical, okay, field. And doctors sometimes can talk to a patient and figure out what's wrong. Okay? Except Chinese, you can never get their emotions. And I've taught, no, at USC, you won't believe it. USC is a private school, huge tuition, Chinese and Indians. Where they get all that money? And my class, sometimes I look at them, I don't know whether they're following or not, and I said, look, you have to tell me, you're paying such a high salary, I want you to learn. No expression. I don't know. And maybe Indians also have, they don't want to offend the professor. I said, you are paying for it. What do you mean offending me? So it'll be very difficult for you to talk to a computer. But that's a hot, very hot field. And military is interested, doctors are interested. Okay. And one of our former Chinese students developed a robot for remote surgery. Da Vinci, have you heard of it? And he sold his company, now he's doing another one. Very bright Chinese guy. We made him a member of the academy, very young. So, hello.
Other questions? Any other questions for
Any other
Professor
questions? Well, it's a pleasure to be back here. I think I should end my story. I came 1967, then I left 1977, and for various reasons. One was very personal, which I cannot tell you. But other thing, I mean, I felt frustrated not knowing where the department is going. And Ralph Meierman and I said, I want to know, where are we going? What is our future? And then Santa Barbara, the call came, and the department chair had exactly the same idea as mine. He knew precisely, and he also was goal to hire senior faculty, because it used to be a teaching department. And so Herb Kromer came one year before me, and he got the Nobel Prize in 2000. And recent faculty member is Shoji Nakamura. He's also part-time with our department, so we claim him also. But that's what I wanted here, bring senior faculty. Then you bring junior faculty, but it was done exactly opposite. So there are a lot of things I cannot tell you. Ralph knows.
We have a chance to talk about that tomorrow.
Right. So,
And a lot has changed too.
yeah, in fact, Ralph, I can recognize the campus. I get lost.
Well, it's a different campus.
Yeah. I have a car. I said, my God, I thought I knew this area. Where are the stores? And I roughly know because my neighbors invited me dinner. And remember Colby Drive, where we was at home. And you were not far from our home, I remember. So, by the way, I saw on the website you and your son are doing some interesting things.
My son is doing different things that I'm doing.
No, you have
But
some.
anyway, one thing I want to mention having to do with signal processing is I'm involved in a company. And definitely it has to do with the man-machine interface,
Right.
which
That's what-
becomes a very important issue. And one thing that is now developing, and we're working with a company unnamed, is gesture recognition.
Yep.
So the way you interact with things, also you can convey impressions. And to an extent, also recognizing some changes in your face. In our case, we're interested in finding when people are moving, but there is a number of things and in fact, there are two problems in there. There is a technology to capture the signals and process them, but also the interpretation of what
Right.
is meant by that gesture.
Actually, Tom Huang at Illinois has been doing this for a long, long time. He's probably one of the leaders in this area. But this is also needed in other areas, okay, particularly medical applications. There's a lot of work going on medical, and DSP is there. USC professor is building artificial retina. You need DSP there, okay. And then another gentleman is Ming Hsieh. I don't know if you heard of him. He's a graduate of USC, came from mainland China, got a bachelor's, master's degree, started a company to identify fingerprint. And you come to the airport, you take a picture and finger, that's his algorithm. And many countries have used this technology. We also made him a member of the academy. I was responsible. Brilliant, and he gave $34 million to the department. It's now called Ming Hsieh Department of Electrical Engineering. And Viterbi, by the way, you know Andy Viterbi, he was working at JPL and he wanted to get a PhD part-time. UCLA refused. He said, no, you have to spend, our UC requirement, you have to spend 9 months academic. US said, no problem. So he has a PhD, and he gave $64 million to USC. He still gave more. So it's called Viterbi School of Engineering. So I hope some of you will give money to UC Davis. Of course, you can give to Santa Barbara. We won't refuse.
Oh, Davis.
No, I said Davis.
Well, let's thank Dr. Mitra again.
Thank you.